Now, following on from this theme of near-Earth objects, I'm going to talk a little bit about the threats to our planet. So we're probably all aware that throughout recorded history, and even before recorded history, throughout its history, the Earth has been bombarded by space rocks, ranging in size, of course, from the sort of the grain of sand size that we see shooting across the night sky as meteors, to much larger objects. So just give me 1 second to set this up, and here we go. And when we talk about larger objects, there have been many famous examples of these. One of the most famous, if not the most famous, of course, is the Arizona meteor crater, formed, it is reckoned, about 8,000 years ago by a meteor that was an iron object that struck the Earth that may have been only about 50 feet across. No remnant of it has ever been found, so presumably it was vaporized in the blast. But that's the famous Arizona meteor crater. Much more recently, in 1908, we had what's referred to as the Tunguska event, where hundreds of square miles of trees were flattened by an object that exploded above Tunguska in Siberia, a very remote region of Siberia. So remote, in fact, that it wasn't until 1927 that an expedition was mounted to go and see exactly what had happened. There were eyewitness reports of a huge fire in the sky, and we think there was possibly one death associated with this when somebody was blown into a tree, or into the trunk of a tree, I should say. But this was, this was potentially disastrous. We don't know the size of the object. No remnant of the object itself has ever been found, because it's assumed that it vaporized when it exploded in midair. The jury, I think, is still out on whether it was an asteroid, a stony asteroid, or the nucleus of a small comet. We really don't know, and there are sort of contradictory bits of evidence one way or the other. We may never know exactly what exploded above the ground in Siberia in 1908, but you can see the devastation it caused. If the Earth had been slightly more rotated, it could have hit a city, and this is always the danger. And in fact, that nearly happened in 2013, again in Russia, at a city called Chelyabinsk, where a huge, a comparatively huge object, about the size of a London double-decker bus, streaked through the atmosphere above Chelyabinsk and exploded. And you can see here the event itself, which was recorded by many people, particularly from dashcam cameras, which the Russians seem to like having. And there was quite a lot of damage from the explosion. About 1,000 people were injured in this detonation, mainly through being cut by flying glass. But here you can see somebody literally being blown off their feet by the blast. And this was a complete shock. Quite a few large fragments of this object were recovered, particularly from a lake where it had actually just sort of gone straight through the ice on top of the lake. But this was a fairly major event, and it did make us realize that this could happen at any time. So this was only 10 years ago, just over 10 years ago. So the statistics of an event like the Tunguska event are reckoned to be can happen in about once every 100 years. But, in just about that time, we had this event in Chelyabinsk. And we've learned quite a lot about the object, but, with 1,000 people injured, it just emphasized just how dangerous these objects are and how lucky we often are that there aren't more casualties. So there is a global network of so-called planetary defense to try and find these objects and chart them and to give us early warnings of any that are coming our way. Daz mentioned Apophis in his presentation, which has a small but finite possibility of striking the Earth at some point in the future. It's making a close approach to the Earth on 2029, and it's not thought to pose us any danger in 2029, but sometime after that it could. We've also got Bennu, which is the most dangerous asteroid in the solar system that OSIRIS-REx recently returned samples of, and that's got a really good chance of hitting the Earth at some point in the future. This is a map of the last 20 years of mapping these near-Earth objects, and there are about 18,000 objects that have been discovered so far. We don't know about them all. The thing was about the Chelyabinsk object that it was completely out of the blue, no pun intended, and we didn't know it was there. And if they come from the direction of the sun, it makes them incredibly hard to spot. But this is a graphic from NASA showing 20 years of studying these objects and what we've discovered. When you look up into the night sky and you think, oh, there's nothing out there between us and the planets or us and the stars, this shows that space is far from empty. So this makes you realize that we are in a cosmic shooting gallery, and collisions inevitably will happen, as they have happened on all the other planets. You may remember Comet Shoemaker-Levy 9 ploughing into Jupiter in the 1990s, leaving those massive scars in Jupiter's atmosphere for a few weeks. And when we look at other planets in the solar system, we see countless examples of impacts, both large and small, and the moon, of course. So impacts can and will happen to the Earth. And it's not a question of if the Earth gets hit by a large object, it's a question of when. So planetary defense is really, really important. We don't want to see something like this. We don't want to see another dinosaur extinction level explosion. And so the question is, what can we do about it realistically? Let's have a look at the hazards by the numbers. Now, if you look at on the bottom, we've got things that look like pie charts. Well, these are pie charts showing an estimation of what percentage of which type of object has so far been discovered. The ones smaller than 10 meters in size, only 0.03% have been discovered. And these are estimated to hit the Earth about once per decade. These can cause damage. These were sort of the type of object that the Chelyabinsk object was. And a very bright fireball, strong sonic boom could break windows. Well, as we saw in Chelyabinsk, it did break a lot of windows and hurt a lot of people. The 50 meter up to 140 meter size, we've only discovered 7% of them for the 50 meter size, and only about 40% of the up to 140 meter size. And although these impacts are statistically going to happen once every 1,000 years in the case of the 50 meter objects, and once every 20,000 years with 140 meter objects, they are still a danger. These are the dangerous objects that we don't know that much about, and we haven't found that many of, but we have good reason to believe there are a lot more out there that we haven't discovered. And of course, it goes up to the 1,000 meter objects and the 10,000 meter objects, which are going to be incredibly rare, once per 100 million years. And this is a life extinction event. Now, over the last couple of decades, the call has been growing and growing for countries to spend more on early warning and identification for these objects. And it's a good sign that over the last few years, if we look at NASA in particular, their budget for identifying near-Earth objects has grown. And I just want to show you the figures of that. We've got two colors here. We've got the observations of the near-Earth objects, and DART, which was the NASA mission to actually try a solution for dealing with these objects. I'll talk more about DART in a moment. But as you can see, the expenditure has risen quite a lot over the last few years as the clamour to actually do something about this danger has grown and grown and grown. Now, obviously, a lot of money still needs to be spent, not just by NASA, but worldwide, in protecting our planet against these objects that could cause disaster without warning at any time. How would we deal with the threat, assuming we've identified an asteroid that is in danger of striking the Earth and causing a problematic event, if you want to put it like that? What could we actually do about it? Well, the first and most obvious option is just to nuke it. And that may seem an elegant and simple solution, an effective solution, but in practice, it's really, really not. The reason is that many asteroids are not solid objects. They are bodies of loose rubble held together by gravity. Asteroid Bennu, currently considered the most dangerous asteroid in the solar system as far as the Earth goes, is an example of this. And here is a picture of Bennu, and it is literally just a pile of rubble. It's not solid by any means. And if you nuke something like this, you risk the danger of splitting it into countless objects, the ones that aren't vaporized. And you only need one of those fragments of the asteroid to hit the Earth, and you haven't solved the problem. You've got a disaster on your hands. So trying to nuke an asteroid and making sure that every last bit of it is vaporized and there are no fragments flying off that aren't going to hit the Earth is a bit of a dangerous business, and there are too many variables for it to be considered an effective option. If the asteroid is solid, like an iron meteorite, for example, or an iron asteroid, or even a solid rocky one, if that is the composition, it might work. But the problem with all of this, we need to know the composition of the asteroid in advance. Another option, which has been suggested, is simply to tie rocket engines onto the asteroid and push it away. Well, this is A, not extremely cost effective, and B, it's not really reliable either. You might end up deflecting the asteroid further towards the Earth than it was originally. So although this has been proposed as a solution, it's not a particularly good one. Another option is the so-called gravity tractor. Now, this consists of a spacecraft which orbits the object, and simply by the gravitational field of that spacecraft, over time, it would deflect the asteroid from its course enough to make it miss the Earth. And this is called a gravity tractor. Now, theoretically on paper, this works. It's obviously never been tried, but the problem is that you would have to have that spacecraft in orbit around the asteroid for probably months before it would have the effect of deflecting it so that it doesn't hit the Earth. And we may not have months to act with these asteroids. Another option, which has been suggested, which on paper works, is to spray paint the asteroid, spray painting it white so that the sun's pressure reflected off the asteroid, reflected off the paint, would be enough to push it slightly and deflect it away from the Earth. This is how a solar sail works. It uses radiation pressure reflected off the solar sail to move a spacecraft. And the idea is that if you spray painted the entire asteroid with say brilliant white, the reaction from the photons bouncing off it would be enough to move its path. But again, this would probably take a long time, and you may not have that time. The final solution is known as a kinetic impactor. It's, apart from the nuke, it's probably the most direct solution, and that is to slam a spacecraft into the asteroid to give it a kick to push it away from its dangerous trajectory towards the Earth. And in fact, this has been tried with the NASA DART mission, the Double Asteroid Redirection Test. And this mission had a very simple concept. The target was chosen as a double asteroid system, a binary asteroid consisting of two asteroids called Didymos and Dimorphos, which are both rubble piles, that is to say, as I said earlier, not solid objects, just held together by the mutual gravitational attraction of all their bits of rubble. And NASA came up with the idea of slamming the kinetic impactor, in this case the DART spacecraft, into Dimorphos, the smaller of the two, which orbits Didymos, to see whether its orbit could be affected by simply slamming a spacecraft into it. It was a very brave and audacious mission, but it was worth trying because we do have to try these solutions. And this happened 6.8 million miles from the Earth. Now, the comparative mass of the two is quite different. The spacecraft, at the time it arrived at the system, having expended most of its fuel, had a mass of 580 kilograms. And the asteroid, Dimorphos, is estimated to have a mass of 5 billion kilograms. So the question is, How could you slam a spacecraft with a mass of only 580 kilograms into an asteroid with a mass of 5 billion kilograms and deflect its orbit, change its orbit around Didymos? Well, the relative speed of these two objects would obviously need to be quite high for it to have any effect. And in fact, the spacecraft did slam into Dimorphos at an impact speed of 4 miles per second, or 6.6 kilometers per second. And if you just want to get an idea of how big that asteroid is, here it is compared to Rome's Colosseum. It's a big rock. Now, this was the launch of DART in 2021. In November 2021, this launched, and it was a perfect launch, a perfect mission. The spacecraft was sent on its way, and this is an image of the asteroid in question, just showing just what a pile of rubble it is, with no real solid surface. It's all made up of just bits of rubble right the way through, not just on its surface, but the whole asteroid is like this, just bits of rock held together by their mutual gravitational attraction. Now, here's the actual last moments of the spacecraft, the 5 minutes leading up to the impact. This is a time lapse, so it's speeded up a bit. As you can see, we've got Didymos coming into the foreground now, and you can see that that is indeed just looks like just a pile of rubble, the same as Dimorphos. We're now approaching Dimorphos at that speed of 4 miles per second, and it's quite obvious that this is a pile of rubble. And these are the last moments of the spacecraft as it slams into the asteroid. That's the last frame. The next frame was not completed because the spacecraft had died, slammed into the asteroid. And this was witnessed from the Earth, from France. And you can see this is on a loop, but you can see the impact observed from the ground and a cloud of debris flying off the asteroid. These are two images of the impact from the Hubble Space Telescope and the James Webb Space Telescope in visible light and in the infrared. Quite a spectacular detonation. In fact, much more spectacular than I think anybody had thought it would be. And did it work? Well, the answer is yes, it did. The orbit of Dimorphos was around Didymos changed. And you can see here that the blue line represents its original orbit and the yellow circle represents its new orbit. It did change quite significantly, and in fact, its orbit around Didymos was shortened by 32 minutes. More than 1,000 tons of material were thought to have been ejected in this explosion. So we have, for the first time, changed the orbit of an asteroid around its parent body. This has demonstrated that the kinetic impactor idea works. And it was a very successful mission, so well done to NASA. On the back of this, NASA have come up with a plan for the future for dealing with these dangerous objects. I won't go through it in detail, but it's basically expanding the observing network to continuously monitor the skies, developing advanced radar and optical systems for precise measurements of these objects, using space-based missions like NEO-Surveyor to increase the detection rate of these objects. NEO-Surveyor is a dedicated spacecraft for finding near-Earth objects that is going to be launched in 2028. Then we've got developing and testing the new technologies, using or exploring various deflection techniques, including the ones I've talked about, additional test missions to repeat the DART mission in a different way with a different asteroid, and getting countries to work together on this threat that does threaten the entire Earth, and sharing the expertise and the knowledge that organizations like NASA have gained. And preparing for those potential impacts, you need mitigation plans, you need strategies for dealing with things like mass evacuations, public education and outreach, which of course we at Space Oddities are all in favor of, and international coordination and cooperation. And the summary of all this is there are solutions which can be used to divert the trajectory of these threatening objects, but a lot really does rest on knowing about the objects in advance, knowing what they're made of, knowing what their mass is, and coming up with an appropriate strategy. There's no one solution for this problem of threatening asteroids that's going to work for every single one that threatens us, because each asteroid in its way is going to be different. So we need a range of strategies that we can apply the correct solution to a particular threat in the future. And of course, we need globally to spend a lot more money on planetary defense. So there you have it. That's
Andy, can I just pop this? I did have another slide.
okay.
Now I know this is out of date because you can see it's, but this is boloid events, as they say, which were asteroids or meteorites that disintegrated in Earth's atmosphere, and this does include Cheslablank in it. And this just goes to show, in this period of just under 10 years, this is how many were reported. And you can see the represented in the sizes along the bottom, and also the ones that were seen during the day and during the night. So as you can see, that was just in 10 years of these things that actually came through the Earth. And
I see it's looking at that. I mean, it's almost evenly split between daytime event and nighttime event.
Exactly. They're coming at us all the time. And this is what we need to know. And these have all been, it's luckily small enough not to cause much damage. The Tugunskas I've done it again. Tugunska event was the equivalent of 10 megatons because it was an airburst, it is thought. Like I said, as you said, they think these sort of events at 2,000 to 3,000 years, to one event every 300 years. The second largest event after Tunguska was a megaton air blast, at 1.1 megaton air blast in 1963 near Prince Edward Island between South Africa and the Antarctic. It was detected only by infrared sensors. However, this may not have been a meteor. Now, this is what I'm saying. The only reason we know about this event, it was detected by sensors. It wasn't actually seen. So, like I said, that image I put up of those 10 airbursts or fireballs that have been reported, that is probably just the tip of the iceberg. And the third largest was the Chelyabinsk on the 15th of February 2013. And as you said, a lot of people, that was sort of like a yield of 400 to 500 kilotons. And of course, like you said, most of the injuries were by broken glass because people saw the fireball move to the windows, and then of course the shock wave hit a bit afterwards. But this is just why we need to be aware, and why we need to try and find ways of mitigating these things. And I'd just like to pop this up from Anne, and she said, we saw a huge fireball going up the Irish Sea in 1969. It landed in in Northern Ireland, partially in a field, and part went through the roof of a police storage shed.
Wow.
It's on display in the Mar Planetarium. Wow. So that was Anne. Thanks for that, Anne. That sparked off a whole load of new chat in the chat. So, yeah.
Great. Fantastic. Thanks, Anne. I would like to have seen that. I've only seen a good few good fireballs in my time, but nothing's ever impacted, as far as I know. So, well, they all impact somewhere, but a lot of them go in the sea, of course, and we don't get to know about them. So there you are. So that's just a little thing from us tonight about planetary defense. The bottom line is the world needs to spend more money on this, and especially governments need to take the threat a lot more seriously than they do. It's not a priority for most governments for fairly obvious reasons, but we could have a disastrous event happening without warning.
I mean, as regards warnings and all that, if the governments know about it, but they don't want us to know about it, just keep an eye on the sales of hard hats. Because the government will all be buying hard hats. Right. So,
and look for elections being called. before the event. Snap elections. Yeah. So there you are. Okay, Lou, are you okay now? Yes, it looks like you're there.
I think we're good.
Okay.
Good. Just two quick comments about
Yes.
all of this. The first is the accurate graphic that you showed with the near-Earth objects in orbit that looked like it was jam-packed, which it was, thousands of objects. That is what it looks like when it fits on your screen. But if you could look at the actual size out in space, you could look anywhere you wanted, and the odds of seeing any one of them would be almost zero.
Of course,
because the space is so large. The other is that for the map of bolides that Daz, that you showed, remember that a bolide that can light up the night sky might be as small as the tip of your little pinky. Okay. Most of the meteor showers that we get are grains of sand size, that kind of thing. So a bolide could be anything from that to something much bigger. Just
to pick up on one of those, Lou, when you see films like Star Wars, where they show spacecraft flying through asteroid fields, where the asteroids are almost touching each other. Of course, if you were to fly around the asteroid belt in our solar system, if you were standing on one of those asteroids, you wouldn't be able to see any of the other asteroids because, as you said, they are all incredibly spread out.
That's right. Yeah.
I'm not saying that there aren't star systems out where there is an asteroid belt where the asteroids are very, very close together, but it's not incredibly likely.